Deutsch.
Sorry for speaking German, because I always continue speaking a language I have started to speak. And on the total, there are 4, and it makes problems. And I was just giving a lecture in German, and now there is another lecture in English. And if there were some Russian colleague here, then I would speak Russian immediately. Okay, let's wait 2 more minutes.
Hello, Professor.
I times L squared, this is correct.
Then you wrote second formula, area per point is equal to n points divided by L square. Area is equal to?
No. Look, if you copied it like this was a mistake.
No, it was, that's the thing, the units does not match afterwards.
Just a second. Just a second. First, let me find my, today at least the connection worked, and I would announce my my iPad as a co-host. Where is it? Somehow I lost it. Here. Okay. And now I continue listening.
Okay. So number of points is equal to sigma into L square, and area is equal to n points divided by L square. So if I substitute the formula for the number of points, then I don't get 1 upon sigma, and you directly wrote 1 upon sigma, but it's actually.
So let's do it together, because what you tell me is not quite correct. So
that's the thing, I was confused when I thought about this afterwards.
Just a second. So now you have the points. Doesn't matter how they're separated. And then if this is L, then the number of points is sigma times L squared, which is a definition of sigma, essentially.
Okay.
Then the area per point is L squared divided by N, which is, if you look here, 1 over sigma. This is the area per point. And the distance, the typical distance between the 2 points, let me call it L small, is then of the order of square root of the, I will call it S, square root of S, 1 divided by square root of sigma.
So yesterday, I think you wrote down on the board area per point is equal to n into n divided by L square. That's why I got confused.
So I don't understand, what does it mean, n into n?
Sorry, I was saying that yesterday on the board, after
this
the
I understood, that maybe I made a mistake, I was too fast or whatever.
Okay, but now
what do you mean? What was written there?
It was the area is equal to n points divided by L square, and that's why I got confused that the dimensions or units don't match, but now they match.
Yes.
Yeah, now I got it. Thank you.
You're welcome. Okay, let me stop this. And now, just a second. I have too little amount of hands. Now I will come to Zoom here, and here I will, Okay, I will go to my own picture, which I prefer, and let me share the screen. And where do I have? This is your homework. This is all your homework. Okay, so I have just to stop it just a second. I have to stop it to open something else. And I don't need your homework, I need the lecture. So I have to close this, this, open this, and then come back to Zoom, and now share the screen. Okay, so hi everybody, and let us go on. So our topic today will be discussion of polymer solutions, essentially solutions and melts. And we will start slowly, and then we will continue next week. The homeworks this week are all devoted to slightly more complex problems which use the concept of blobs, because we all, I think, got a feeling last week that we need more training. So there will be 3 problems. You can have a look after the lecture, and 2 of them are very similar. One of them also slightly tangles the class of problems we discussed today, but only slightly. So let us go on. Let's continue. So now, up to now, we discussed essentially single chains. It's not a very, it's an interesting object, but it's not a very important object, let's say, from the point of view of whatever, of technology, of life science, of whatever, because you have many of them. You always have many of them. Now let us consider the simplest situations where you have many chains. And I will start from classification pertinent to the case of a thermal solution, and then I will go into the corresponding situations, into introducing some approximations for the general case, and then we can return to the question how general my classification was. But at least at the beginning, I think it's important to understand the scales. So what is a solution? What is a melt? What is a concentrated solution? What is a dilute solution? And what is what? And here, let me again stop the screen here and draw a picture. Just a second, and I will draw a picture. So imagine you have a vessel in which you have some polymers. So this is a vessel. And now imagine you have an athermal solution, simply because we know what is the size of a self-avoiding walk in an athermal solution. It's the Flory radius. And let's draw a few polymers here. So essentially the polymers are inside of these circles, or essentially balls in 3 dimensions. So now what we see here is that I have n molecules. I don't now remember because I closed the window where I had a script. I have n molecules, or let's say, let me call it n small n. Yes, I have small n molecules, each consisting of capital N monomers, and which means that the characteristic size of each this molecule is of the order of the Flory radius, which is an to the power of nu. So there are some characteristic sizes. Now, if I draw more and more molecules, then at the beginning, they hardly interact. They are typically far from each other, and if two of them are by chance close to each other, they collide practically like solid balls and flow away or fly away. So this is a regime when the typical distance between the two molecules is much larger than the Flory radius, then this is a regime of a dilute solution. The molecules do not overlap. Then, if I draw more and more molecules, yes, they start to touch. And I have some characteristic concentration at which my whole system is filled by the molecules which fill each other. And here I come into the regime of a semi-dilute solution. A concentrated solution is the case when there are so many molecules, monomers, that they are practically everywhere. Now, let's go to my, just a second. Let's go back to my script. And what I have drawn on in the picture is essentially what I write here. So I have a lattice of volume V with, if you want, n0 sides, m sides, whatever. I have polymers of n repeated unit each, and I have n such chains on the total. Then if I divide this guy by this guy, I will get the fraction of the occupied sides. And if I calculate everything not in sides, but in the units of length, I get this concentration of monomers per volume, which is exactly this guy divided by A cube, divided by the volume per monomer. And this is one important thing. The concentration of molecules, of polymers, is smaller by the factor capital N. And now let us have a look at what happens whether I have now this situation of a dilute solution where the molecules do not intersect typically, and when they do intersect. And then I see that the concentration of molecules, which means of the polymers, at which the intersection starts, is of the order of 1 divided by the cube of the Flory radius. It is as if you had now a packing of hard spheres of balls of the size R Flory. And it depends on the size of the polymer as a to the power of -3 n to the power of -3 nu. Is the concentration of monomers or of polymers, sorry, smaller, they do not overlap. If it is larger, they do overlap. And the concentration of monomers is essentially the same multiplied by n. So maybe I have a formula, I don't have it here, it will have here, yes, it's here essentially. N to the proportional to n to the power of minus 3. So at very small concentrations, I have a dilute solution, and the chains can be considered as non-interacting. They're separated by large distance. Then I come into the domain of a semi-dilute solution, where the interaction between the chains gets considerable. But if I count the number of monomers, or the concentration of monomers at this characteristic concentration, so the concentration of monomers phi corresponding to the beginning of overlap is n to the power of 1 minus 3 nu. Nu is 3/5. 9/5 is larger than 1. So I have here 6/5. It's practically n to the power of minus 1. So if the molecules are long, the concentration of monomers on the onset of semi-dilute regime is extremely low. So these semi-dilute solutions are characterized by the fact that the molecules do overlap strongly, but the concentration of monomers is still very low. And then if I go up with the concentration of monomers, I come into the domain of a concentrated solutions, when phi is of the order of unity. Let's say half of the volume is occupied by monomers. And then if the whole volume is occupied by monomers and there are no solvent molecules there at all, I come into the regime of a melt. So this is the classification. So I have now a system in which the concentration of chains is large, but the concentration of monomers might be large or small. Now, this is the terminology. So in the case of a solution of small molecules in a low molecular weight solvent, I only distinguish between the limiting cases of dilute and concentrated solutions. And here I have this very non-trivial semi-dilute regime, which is in many cases interesting. So up to now, we considered what happens with molecules in the dilute regime, where they do not feel each other. Then we will consider what happens with the total solution in different regimes. And then after we consider this, we will consider what happens with a single molecule in different cases. We will come to a single molecule again. Okay, wonderful. Before we start with the model of polymer solution, I decided to return essentially to our lattice gas model and to show some tricks here and to discuss some important things. And for this, I will discuss a very slight, a minor simplification of our lattice gas model, namely a binary alloy model. The model is more than 120 years old, so it's an old variant. So let us consider again a lattice model which is practically the lattice gas. So it's here. If I say that the white sides of my lattice are empty and the black sides of my lattice are filled with molecules and no double occupation is possible, this will be a lattice gas, which we already discussed. Now, instead, I say that I have not, the sides are still of two types, but they are not empty and filled, but they are all filled with atoms A or atoms B. For example, you can have the copper and gold atoms, or if you want, I don't know, copper and zinc, and then what you get is bronze, whatever. So it's a binary alloy. You have molecules or atoms of two types. Now, the entropy of your system, or the number of configurations, the number of arrangements of atoms in your system, is exactly the same as in the lattice gas. Because what I did up to now is simply renaming. What I called occupied was gold, is gold, and what I called empty is now copper. Because gold is, you know, expensive and copper is cheap. Not so cheap, but still. So I know the entropy in the lowest relevant approximation. I simply already know that to calculate the thermodynamic entropy, I don't need the higher terms or the higher corrections stemming from the Stirling formula. And essentially for the future, I can also put it as follows. Now it was filled, it was empty, yes? And now I say I have n, small n of type 1, and I have capital N1 of type 2, so to say. And here this is empty, this is filled. And look at the total structure. The total structure is always n ln phi, with n's and phi's corresponding to the correspondent constituents of your system. And now it's also easy to guess what happens if you have a ternary alloy, a more complicated mixture. It will be N1 ln phi 1 plus N2 ln phi 2 plus N3 ln phi 3 plus blah, 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 blah. And each of these terms, which are added in the slowest order in the formula of the entropy, are called the translational entropies of the corresponding constituents. Now, however, what is new here is that while in the model of a lattice gas, the atoms of the same type, they did interact because they didn't want to let each other on the occupied place. But this was an athermal interaction. It's zero or nothing. So to say, it's either impossible or possible, and then the energetic contribution is zero. Now the atoms interact. The real atoms interact, and the real atoms can either attract each other or they can repel each other. And for example, in a metal lattice, on the average, they attract each other because, you know, a piece of metal somehow keeps together, is kept together, of course, by the attractive forces between different atoms. The true nature of the forces is complicated, and in metallic bonding is a complicated thing. These are collective forces, but it doesn't matter. We are playing with the simplest possible model, which essentially, in many cases, was proven to give semi-quantitative or even quantitative predictions. So it's a nice model. And now let us calculate. So in all our previous situations, which were thermal, we said, so normally, let me share another screen with you. Just give me a second. Here I have my pencil. I would like to write something. So we have written F is equal to U minus T times S. And since where U is the internal energy, and since our internal energy did not depend on anything, this means athermal, we simply neglected it. And in all our, or say it's a constant. So we have written F is some constant minus T times S. But now you have real interactions, and U depends on the placements of your molecules on the lattice. For example, if you have here everywhere A atoms, yes, and here everywhere B atoms, you have a different interaction than you would have if you have, for example, A's and B's interchanged, somehow alternating in your lattice. I will not draw the whole, but I draw an example. So here the energy will be different. You have different interactions. Here you have atoms which meet with each other, atoms of different type which meet with each other only here close to the surface, and here it's everywhere. And we have somehow to take this into account. And we will try to invent, which means that the two very clever gentlemen, Mr. Bragg and Mrs. Williams, at the beginning of the 20th century, invented a very simple model in which we assume that first interactions are only short-ranged, so that we assume that only the neighboring atoms or atoms occupying the neighboring sites do interact. And then we can easily calculate the internal energy in this system, which does now depend on the configuration of your system, the configuration of the atoms in your system. The interaction here is always pairwise. The atoms interact with each other, namely here with the neighbors. And essentially they are, in this model, three different interaction energies, local interaction energy. If you have an A-B pair, if an atom, let's say B, is a neighbor of atom A, their interaction energy is epsilon AB. It's or EIB, doesn't matter. I put epsilons there, let them call epsilons. If there are two atoms, two A atoms, which interact along the bond, then the bonds now represent interactions. Then the interaction energy is E or epsilon AA. And if there are two B atoms along the bond, the interaction energy is EBB or epsilon BB. Now the total internal energy, if I neglect the kinetic contribution, but I can always do this in the classical system because it's kBT per degree of freedom, it doesn't depend on configuration and therefore doesn't show up in the final results. It is there, but I simply forget about this. It stays in the constant. So here I have this guy as my expression for internal energy, provided indeed I can describe the interaction by local interactions of neighboring pairs. Let's assume I can. Now, let me try to estimate these NAA, NAB, and NBB. These are the numbers of pairs or the numbers of bonds, because energy interaction is pertinent to the bond, which connect correspondingly to A atoms, an A atom and an B atom, and two B atoms. And now I'm going to this estimate. So what I know is the following. Let C, in my case 4, be the coordination number of my lattice. And now imagine I have an A atoms, and an B atoms. Now let me take a site which is occupied by an A atom. And I consider all the bonds emanating from this site. since on the total I have Na sides, there are C and A bonds emanating, outgoing from the sides where there is an A atom. And now I say that this total number of bonds emanating from A sides is twice the number of bonds connecting to A sides plus once a number of bonds connecting A's and B's. Do I need to show a figure? Essentially, these two, I don't essentially need, but now I am counting all bonds with one end starting at A side. If on the other side there is another A side, this bond is counted twice. If there is a B side here, this bond is counted only once. So I obtain this equation. Hope it's clear. If not, draw a picture yourself. Then by symmetry, it's the same for B. And this means that essentially with the number of A and B atoms fixed, I have only one free parameter, which governs NAA and NAB, and this is NAB. This is the number of bonds or the number of pairs consisting of two different atoms. And now I put this expression here into my expression for the internal energy. And this is what I get. Now let us look at the terms and enjoy them. Because what is this? This is the following. Imagine you have a lattice of Na sides with all sides occupied by A atoms. Then this guy is the total interaction energy in such a system, because this is a pure A, let's say crystal or maybe fluid. This guy is away, and this is the internal energy of the pure A substance. And this is the internal energy of the pure B substance. And this is the correction in the internal energy to these pure substances due to interaction. Now, these guys, since if you have a solution or an alloy or whatever, the atoms do not go in, the atoms do not go out, this is a constant. We have now the interpretation, the physical, if you want, chemical interpretation for this constant, but this is a constant. And this guy can change if the atoms A and B can rearrange. And now let us have a look. First, what will be the situation if they do rearrange? So in the case of the pure solution of the pure substances, let me come back here. Yes, let me just come back to my drawing, because let me come back to my drawing, and I come back to this picture. Imagine that this is in 3D, and essentially this is a cube, and it's huge. The total amount of atoms is very large. Yes, Then I have the volume here with the total of Na atoms, and here I have a volume with the total of Nb atoms. And if the concentration is given or A is given, then this is, let's call it V1, this is V2. Let's say the half A, half B, this is L. So I will have Nb equal 1/2 L cube divided by A cube, and then A 1/2 L cube divided by A cube. And the number of contacts with the atoms of the other side, of the other type, they are all these contacts are only on the surface. And the number of contacts in AB will be of the order of L squared divided by A squared. This is the number of atoms immediately below or immediately above the surface. And this, for large L divided by A, is considerably smaller than this. So in the case of separated, so to say, substances, NAB is very small. If I have a configuration in which the atoms alternate or in which they are taken at random, 1/2 of the contacts are the contacts with atoms of another type. And this I will always use in my further considerations, and I will compare these ordered situations, A and B, so to say, separate, with the disordered configurations of A and B mixed. So now let's go into the question, what happens if they are mixed? Now, if they are mixed, I can say that at one end of the bond, I have one. At another end of the bond, I have another. NC is approximately the total number of the bonds. Okay, NC half, I have probably forgotten the half. Because for each side, the bond is calculated twice. And here I have phi, 1 minus phi, it's essentially Na times Nb, the total number of AB pairs. No, it's correct. Sorry, it's correct. It's the total number of A's times the total number of B's, because this guy is this is the product of the probability that a site on one side of the bond is occupied by A, and the site on another type of the bond is occupied by B. And now I put down the total free energy of my system. I will have to check whether there is no 1/2 there, but I think there is no 1/2 there because I already have 1/2. Correct, I have 1/2 here. This guy of 0 comes from U0, from the internal energy of pure substances, and from the constant term in the entropy. And this will be from here, and this will be absolutely uninteresting for me in what follows. And the rest has a structure, something, this energetic parameter, times phi 1 minus phi, the probability, if you have a disordered situation, the probability to have a pair of two different atoms, and then this sum of translational entropies of your system divided by KBT. Now, since this is uninteresting, I can also divide everything by T, F divided by T, or I can put t to the outside, and then I have this guy divided by t, phi 1 minus phi, and this guy divided by t is called the Bragg-Williams parameter. So it was there, and it's a nice theory which you can essentially pursue further and get quite satisfactory theory for binary alloys, which describes what happens with the alloys, when do they phase separate, or if you want to describe the low molecular weight solutions where both components are low molecular weight, and when they are miscible, when they are not miscible. And essentially, it's quite a reasonable theory on the semi-quantitative level. It works. And when people started to build theory for polymer solutions, they had this example. And they worked according to a pattern. And the pattern is exactly as I described here. You will then play a little bit with this simple model because it's slightly simpler than a polymeric model with some respects. This will be not the homework for this week, but the homework for the next week as one of the homework problems. And now the model or the variant of the Bragg-Williams model for polymers is called Flory Huggins model. These are two independent guys, and they did it separately. And this is indeed the simplest approximation. It works wonderfully in two regimes of a dilute and concentrated solution. It works qualitatively well in the semi-dilute regime. It is quantitatively not quite okay in the semi-dilute regime, but it's absolutely sufficient to explain what one sees physically. So it gives a correct qualitative explanation of what happens, just a second, of what happens in just a second, of what happens in different regimes in polymer solution. And I will tell you where the main approximations or main deficiencies are, and I will tell you that some of them were overcome, but I will not, again, as often in this course, I will not show how. Because then things relatively fast get relatively complicated mathematically. So now what is the difference between the Bragg-Williams, between the binary alloy and the model with chains? Now I have here, let's say, my type A atoms. They are connected by the chains. They always sit in connected clusters. And I have to take this into account. Why? This is because I can hardly move these atoms separately. To see this, let me have a look at the total number of possibilities to make the arrangements. So this is what we already discussed in our combinatorics in the beginning. Something is very simple. So it's the overall number of permutations of how you can choose the sites before placing atoms. Then imagine you have placed the molecules, and then you place in the rest N1 sites, which are not occupied by the molecules, you place the atoms of the solvent, of the low molecular weight solvent. And there are and 1 factorial permutation. This is what survived from the simple binomial formula which we used here. But the number of ways to place the molecules and to place the monomers within the molecules is now changed. It is strongly affected by the fact that you cannot place the atoms in a molecule at random. They are connected by the chain. So what do we know is the following. First, of course, also the molecules, when you start placing the molecules on the lattice, they affect each other, and you cannot place a part of this molecule onto this molecule because the sites are already occupied. Let's forget it for the time being, because it is essentially a minor effect. A major effect is the fact that you cannot move the atoms in the molecule at random. The total number of ways in which each molecule can be organized if the other molecules do not disturb is here. This is what we discussed yesterday. The first atom of the molecule, the beginning, can be placed everywhere. But the rest is confined. And now if you take the log of all of this, the log of this is a constant. And here you have the number of placements of the beginning of the molecule. So essentially what you get is, the number of the beginning is the number of monomers divided by the length of the molecule. What you get is the configurational entropy with the contribution of the polymers, which is practically n times smaller than as if it would be if the monomers would not be connected by the chain. So what we here neglected fully, okay, the number of conformations within the chain went into the constant, but we neglected fully, of course, the hindrance of one molecule by the other molecule. And this you can correct for. This is the so-called Bavendi-Fried approximation. But again, you get some things which you understand how they work only after you have understood the Flory Huggins, the simplest approximation. These are higher corrections to these approximations, both in the entropy and in the internal energy. Now, let's assume that this is now our entropy. This is translational entropy of the monomers, number of the monomers, log of their concentration, not the monomers, but the solvent molecules. Number of the solvent molecules times log of their concentration. And this is, it's essentially exactly the same expression, but for the polymer molecules. This is number of polymers, and this is the concentration of their beginnings, of the points on which you can move them. Therefore, it's translational. It's how can you move them in space? And for the time being here, for the internal energy, we, on the contrary, fully neglect that they are on the chain. We say, you know, it doesn't matter. They're still well mixed. So in one situation, we exaggerate the role of the chain because we consider these polymers practically as solid objects, while they are not solid. And in the other sense, we consider them as essentially the assemblies of loose monomers, like here, like the bags of monomers, not like the monomers on the chain. And we put down the same expression for the internal energy. And as it is always the case, not always, but often the case, somehow grave errors compensate. So you do very, very rough approximations, but at the end, you obtain something which is okay. It's not exact, but it is of great simplicity. And then you understand what happens, and then you can go into minor details, into making perturbations, and so on and so forth. So now we have our expression for the free energy. And we call this guy, which is this guy, divided by T, the Flory Huggins parameter. And now we have the free energy of our system expressed via the number concentration of monomers only, or the fraction of sites in our lattice model occupied by the monomers only. The thermal solution corresponds to this guy 0. We will go into this also later. And now let's play a little bit with the model. We will consider the model and its relatives in detail next week. And this week, I only would like to do one simple thing, or today I would like to do one simple thing. Namely, I would like to calculate the osmotic pressure in polymer solution within this Flory Huggins model. And this is essentially easy, but maybe not as easy as it seems. And then you can also calculate the osmotic pressure within the blob model. If you do not succeed in the last exercise of the homework, we will consider it anyhow in the next lecture. Just think about it. And let's go on and let's calculate the osmotic pressure in our system. Now, what is here the problem? We calculate here the osmotic pressure, and the osmotic pressure is dP over dF minus dF over dV. This we know. So it's essentially a pressure is always the minus the derivative of the free energy with respect to the volume of your system. However, we do not simply take the derivative. We have to take care of the fact that the number of monomers in the system stays fixed while the volume changes. Because the monomers, if I come back, just let me stop it for a second and try to draw the corresponding figure to explain you what happens. Sorry. Here. Now, how do I measure osmotic pressure? I have a vessel. Yes, and I have in this vessel a semi-permeable membrane through which the solvent molecules can go in both ways. It's absolutely permeable for the solvent, but it is not permeable for the polymer because the polymers are huge. They do not pass through. It's a kind of a sieve. Now, when I vary the position, so varying the volume is simply moving the piston here, the semi-permeable piston. When I vary the position of the wall of the semi-permeable membrane, all monomers, all polymers and all monomers, they all stay here in the left side. And there are essentially several ways to take this into account. And just a second. To take this into account, and to my taste, so of course you can simply put now express here F via V without forgetting what V is. So you put instead of phi number of monomers divided by n0, and you recalculate n0 via the volume. And then you will have the volume everywhere, and then you take the corresponding derivative. But it's lengthy. So what I do here is the following. I do not play with this form. I take this form as it is. It is not the free energy in its natural variable with it, which is volume. It is a free energy as a function of volume expressed via an Allan variable phi. But as a function of phi, this expression gives you the correct numerical value of the internal energy. Now I simply use here, first I calculate the internal energy per site, and then because this is a very nice function, it does not contain n0. It does not contain any general properties of my system. It only contains this phi, and then I take a derivative of this, which would be a numerical value, a number value of the free energy per site in my system with respect to the volume. And what I do here, I use the formula of the differentiation of a composite function. So what I have, n monomer, n0 is n monomer divided by phi, because it comes from the definition of phi. It's here. And d phi over dv. So it's simply a chain rule of differentiation of a composite function. And the only thing I have to take here a derivative with respect to phi of a universal function f of phi divided by phi. So I take the guy divided by phi and take a derivative, and this guy is essentially very simple. So now I rewrite it. So this is the second derivative, it's phi squared. And now if I take this derivative here, d phi over, I take a derivative of this bracket, and I write everything explicitly here. And I hope nobody would have any difficulties with reproducing this. It's simply differentiation, d over d phi 1 over phi 1 over phi squared minus times phi squared, it's minus phi squared, and monomer cancels. It's a wonderfully simple expression. And this guy, the derivative of phi, is very easy to take because phi is essentially, this is a quadratic function, and these are these logarithms where most of the things cancel anyhow. So this is the expression. It's very simple. Now, this is the standard expression for the ideal gas. It's ideal gas of polymer molecules, as if there were no interactions, no molecules. And these are corrections. These are essentially the V-real, this is a V-real expansion for the corresponding osmotic pressure. Wonderful. Now I do the true V-real expansion in that I consider what happens if I expand the logarithm in series. So log 1 minus phi is minus phi square half minus phi cubed 3, and it was minus in front, so it's like this. There is, of course, phi cubed, phi to the power of 4. Now they are not very interesting for me. There are cases when they play the role, but they're not interesting. And now let's have a look what happens here. I have here, what did I lose? Yes, these guys, the first terms, cancel. And the only thing which stays is this linear term, the ideal gas, and the quadratic term with a prefactor high minus 1/2. Now, let's have a look at the thing a little bit. First, if high is equal to 1/2, this guy is away and it starts from the cubic term. I don't consider it, but now, I don't consider it now, but the case high equal to 1/2 is an important case, and it's called the case of a theta solution. Just a second. Now again I have a break. Now again I have the problem. Just a second. But maybe okay. There is a connection problem again, reappearing. First time today. And this is not very interesting now, but there is a specific situation, a very special situation, which is called theta solution. We will see why it is interesting. It's essentially a very distinguished situation. Many things happens there. There is a border between good and poor solvents. And now what is important to keep in mind is that according to the definition of high, I have a possibility to change the value of high by changing temperature. I can never change the sign of high, because the sign of high is given by the sign of this expression. So if high is positive, it is always positive at whatever temperature. If high is negative, it is always negative. But when high is positive, working at high temperatures makes high smaller than 1/2, and then I am in a regime of a good solvent. And when temperature is very high, high is small, I come to the thermal regime. And if the temperature is low, high can be very large, and I am in the regime, if high is positive, in the regime of a poor solvent. And solvents with high smaller than the pairs, solvent, solute, with high smaller than 0, they always stay in the good solvent regime. Now let us have a look what happens at moderate concentrations. So this guy is much smaller than phi squared. This means that the concentration is moderate. If this guy is the only one, then it is, if this is small, it's an ideal gas. It's a dilute case, essentially. Now, this guy is larger than this guy, but smaller than unity. We are not in the concentrated case. So then I have something like this, and I have that my osmotic pressure is proportional to the square of the concentration of solved molecules. And this is essentially something corresponding to a semi-dilute case. Now, first, as we will see, in the thermal situation, this will be a homework which we will consider during the tutorial next week. We will see that in the thermal case, the formula is not quite correct. There is a different power here. The power differs not by large. Instead of square, it's 9/4. But there is a difference, and one can measure it. Another thing which is interesting here is what happens if high passes from above this magic value of 1/2 for a theta solution, for a theta, from below this magic value of 1/2 for a theta solution. If high is smaller than 1/2, then the pressure is positive. And it's okay, we know that the pressure has to be positive. If high is larger than 1/2, you get here a negative pressure, which is nonsense. You know that from the criteria of thermodynamic stability, the pressure cannot get negative. So this means that something is fishy there, and it's clear what is fishy. This theta case describes the transition, and therefore I decided to show it now, the transition from the regime of a good solvent, in which indeed you can assume that polymers and monomers mix together, and there are enough contacts on my picture here between the monomers of a polymer and the solvent molecule inside of your system. And in the other case, for high smaller than for high larger than 1/2, when the pressure given by this formula gets negative, which is a nonsense, something happens. Namely, you come into the domain of bad solvents. My thing doesn't want to. I have to close it and to restart. Let me try to restart it. Now it works again. Wonderful. When the molecules, the polymer molecules essentially try to separate from the solvent. We will discuss it in a week or so. Let me draw a picture. Now let me stop it here. I simply will explain you what happens. Let me share. I don't know whether it's still a co-host. No. Co-host erstellen. Now let me draw a picture simply to explain you what happens. So what we had there is that in the case of good solvents, this is high smaller than 1/2, or if you want, smaller equal of the water. You have, this we will see, you have the molecules. Wait, everything is very slow. We have again the connection problems. Yes, now we have the molecules here, which are very loose, we know, like self-avoiding rock, which are very loose objects, huge, and everywhere inside there are the solvent molecules. So I can say that the polymer and the solvent are well mixed. Now let's wait until my wonderful drawing appears. Now it's here. And this is a case of a good solvent. In the case of a poor solvent, which exactly appears when I gets above 1/2, the situation is very different. And as we will see, the molecules want to separate from a solvent. And now let's wait until the picture appears. Oh, slow. They don't want, they are essentially repelled from the solvent molecules, or if you want, the solvent molecules are repelled from the monomers. And the monomers in a polymer make a kind of a droplet, which are called globulae. So now we have these globulars. Within each of them, there are hardly solvent molecules inside. So now I have an ideal gas of globular, essentially. And my assumption, which I put as a foundation of my approximation of this Flory Huggins variant, it doesn't mean that I cannot come to this regime with Flory Huggins. It means that my naive use of Flory Huggins didn't work. So my naive use of Flory Huggins approximation now does not work. And I must do something else. But we will see this. Now, in the case when the concentrations are very large, what survives is this logarithmic term, because it diverges. If phi approaches unity, the logarithm is the largest term. This 1 minus phi is close to 0. The logarithm is huge. This is 1. This is of the order of 1. This is small anyhow. So I get the logarithmic term. And this is again okay. If you measure it, you see. So in the dilute regime, the Flory Huggins approximation gives you the correct result. Any dilute system behaves like an ideal gas. In the concentrated regime, it gives you something which is okay. This is logarithmic. And in a semi-dilute regime, it gives you this quadratic approximation, which is good. It's not excellent, but it's good. It's qualitatively correct. But the approximation breaks down in the case of poor solutions, which are characterized by the value of the Flory Huggins parameter, which exceeds 1/2. And now I think it's enough for today. And I will close the screen sharing and ask you whether there are questions. Do we have to discuss something?
I have a quick question.
Yes.
Okay. The epsilon term that it's in many formulas in this lecture,
Yes.
what it exactly means?
Now look. Exactly, it means the following. Now there is here and also before in the Bragg-Williams, we now take into account the interactions between these two atoms.
Yes.
Or between the monomer of a chain and a solvent molecule in a solvent. This interaction is assumed to be short-ranged. And with this interaction, there is some energy of interaction connected.
Okay, okay.
So it's the energy of the pair interaction.
Okay, now I understand. Thank you very much.
Do you need something more on this, some more details, or it's okay?
It's okay.
It's
I
okay.
just had
Wonderful.
this question of how are all the terms, so I can understand better the equations. Thank you very much.
So these are simply the energies of interaction of the nearest neighbors. They were absent in the lattice gas. The rest is the same, but the interaction energies in lattice gas were absent because empty places do not interact anyhow. And the atoms were not considered, the atoms of the gas were not considered to attract each other or to repel each other if they are neighbors. They were only considered not to be able to occupy the same site, which is a pure excluded volume interaction. But you can also introduce there the interaction, then it will be, so to say, lattice real gas.
Okay,
Okay,
interesting. Thank you.
you're welcome. Other questions?
Yes, Professor, can you again explain the when the Flory Huggins model started, the W formula, like the explanation I could not follow.
The explanation you could not follow.
The W for the Flory Huggins model.
So we say the following. Look, let me again share the screen and draw a picture. Now, you know, we are, just a second. Where is my pencil? Here. We start on a lattice. We have a lattice. And now we calculate the total number of possibilities of placing there the solvent molecules and the polymers. And we know that let's look first at the placement of the polymers. Essentially, if we have the placement of two kinds of objects, you have normally this binomial formula. W is n, let's say 0 factorial, n factorial, n large factorial, doesn't matter, and 0 is the total number of sites, and n plus n is exactly n0. This is the binomial formula. This you know from our lattice gas.
Yes.
Now, I got the intuition, or we have to get an intuition, that the total number of way in W in which you can place objects is the number of renaming, so to say, relabeling of all possible position, this stays, divided by the number of configurations, so to say, of renaming, so to say, of one case, one kind of the object, so it stays. But now here I have problems. I don't have any renaming anymore, or any simply exchanging of the monomers in a molecule anymore. So what I have, what I can do for free, I can put for free the beginning of the molecule somewhere. So and here I have the number of ways to place molecules. So essentially it's number of ways to number the sites, number of ways to place the solvent molecules, and this is number of ways to place molecules. This is my interpretation of this formula. Did you get it or not?
Little bit.
Little bit. Okay. Let's assume you got it. So now let us look into this more carefully. So now what is the number of ways to place a molecule? It's a number of ways to place it beginning. And on the total, there are phi divided by n times n0 ways to place the beginning.
Okay.
And then there are ways to place the rest, but these are very much restricted. And there is on the total a constant number of placing this molecule for fixed number of monomers. If this guy, if the beginning is fixed, then the number of ways to place the rest is c to the power of n, n to the power of gamma. And this is essentially a constant.
Okay.
So I can now place here, this is my approximation. I fully neglect the fact that I have to prevent the molecules to cross. And I only consider something like this. W is approximately n0 factorial, the number of ways in which I can renumber the sites, divided by the number of ways in which I can renumber the empty places or the solvent molecules. And here I will place number of molecules factorial, just a second. Ich habe Vorlesung. The number of ways to place the molecules. This I can do for free. And for which of these ways I have this guy here, which is a constant. And then when I take the logarithm, this goes into the constant part, and this is at the end what I get there. So essentially what I'm doing here, just let me say it once again. What I'm doing here, I am considering the molecules as solid objects. And now if you use your, let's say, binomial formula, it doesn't matter in which dimension. Yes, let's consider it in one dimension. This is a lattice. And imagine that in this lattice, you can place the solvent molecules as you want, and the dimers. So your polymer takes two sides. Just calculate the number of ways you can do this. And this is exactly what you obtain there.
Okay.
I do not take into account two things. The fact that the molecule has many conformations, because this many is not so much to change considerably the form of the entropy. This is one thing I neglect. And second thing I neglect is that the molecules can hinder each other. But now look, if I neglected the first, the total number of, so to say, conformation of this guy, I fully neglected the internal orientation, I can also fully neglect the fact that they cannot cross, because this crossing essentially is simply forbidding some special kinds of internal orientations. So the only thing by which the molecule is described is the position of its beginning. And if you play with solid objects, you will see that this is exactly the approximation. For example, if you have a lattice and you try to place, for example, on this lattice, the squares without self-intersection. This is exactly what you will get.
Okay.
Okay, wonderful.
Thank you.
You're welcome. Are there now let me close here. No, don't want breaking. Just a second, I close my screen here. And there was a question in a chat. F larger than 1/2 means that the solvent is poor. Is it possible to explain using a lattice model? What do you mean under is it possible to explain? This is my question to you. We have seen that at chi equal to 1/2, something happens. And the naive variant of our model gives us a stupid result, which means this is a domain where the model doesn't work. We will see what happens there indeed, because a slightly cleverer variant of the model gives you a correct result, namely a very good one. But I don't, I don't understand what the word explain means here. I have here something which depends on the interactions, and for some specific case, specific strength of interactions in relation to temperature, something happens. And this is a true physical effect. And we will see what kind of effect is this. This is essentially demixing. Are there further questions? Since I don't hear any and I don't see any, let's say goodbye to each other and let's meet next week.
Okay, thank you. Bye.
Thank you very much. Bye.
Thank you for coming.
Thank you.
Bye.
Bye.
Oh, let's slowly close it.